الشبكة العالمية للعلماء الجزائريين إيناس هي منظمة غير ربحية تأسست عام 2016 من قبل أكاديميين ومهنيين جزائريين مقيمين في الولايات المتحدة الأمريكية. الهدف من وراء تأسيسها هو رد الجميل للوطن والمساعدة في رفع مستوى التعليم في الجزائر. مهمة إيناس هي ربط الكفاءات الجزائرية في جميع أنحاء العالم مع نظرائهم في الجزائر. من بين أنشطتها نظمت إيناس مؤتمراً مهماً عقد خارج العاصمة واشنطن في الولايات المتحدة الأمريكية عام 2019. حدد المشاركون في المؤتمر عدة قطاعات حيوية تحتاجها الجزائر، واتفقوا على العمل في 10 مشاريع تغطي مجالات مختلفة نذكر منها التعليم والرعاية الصحية والزراعة والسياحة البيئية إلى آخره. والعمل في هذه المشاريع لا زال قائما. تستخدم إيناس أكثر المناهج العلمية تطورا من أجل تسيير ومعالجة هذه المشاريع. البداية المتواضعة لإيناس تضمنت عددا قليلا من الأعضاء، وهي اليوم تضم مئات الجزائريين الأكفاء من جميع أنحاء العالم. هدفهم هو المشاركة في رد الجميل والمساهمة في بناء جزائرنا الجديدة. هذه الثلة من الكفاءات الجزائرية الفخورة بوطنها تجمع بين التنوع والخبرة مع الاستعداد والرغبة في تمهيد الطريق من أجل مستقبل مشرق للجزائر. تستخدم إيناس منصة تقنية جد متطورة تسمح للأعضاء بالتعاون وتبادل الأفكار والخبرات. كمنظمة قائمة، إيناس لديها أقسام عملية مختلفة تضمن الدعم المحترف لجميع أعضائها ومشاريعها وتظاهراتها العلمية. نرحب بكل الكفاءات الجزائرية في العالم للانضمام إلينا في هذه المهمة النبيلة. الجزائر أكبر منا جميعا، فلننهض ولنترك بصمتنا.
Hello and welcome to everyone joining us in today's special and exciting event, Potential Geothermal and Resources in Algeria. So following the series of the new project, Advances in Geoenergy and Renewables, I'm your co-host for today's webinar, Qamardin Aisu, structural geologist graduated from the University of Science and Technology, Huawei Boumediene. So mainly the goal of the project is to provide university students and young professionals the technical background to understand the technology used in the energy sector. So that is to move and cope with the challenges faced and to move into sustainable and cleaner energy in Algeria. So without further ado, let me introduce you to the leader of the project, Dr. Mohamed Arbrouche, and his special guest and keynote speaker, Dr. Hakim Saibi. Welcome, everyone.
Thank you, Qamardin. Thank you very much for the openings. Thank you, everyone, for joining us. Today, we are very excited to share with you one of the very interesting topics, which is geothermal energy in Algeria. So today, our guest speaker will be Professor Saibi Hakim. Professor Saibi Hakim, good afternoon. Thank you very much for joining us, and thank you for accepting our invitation.
Assalamu alaikum. Good afternoon. Thank you.
So Professor Hakim Saibi was born in 1976 in the Sidi Aish Wilaya of Bijaya in Algeria. He is a professor of geophysics and geothermics at the Geoscience Department in the United Arab Emirates University in the UAE. He holds a BSc in Ingénieura d'État en Hydrogéologie and a Master Magistrat en Hydrogéologie in the Earth Science from the University of Science and Technology, Huawei Boumediene, UST Algeria, and a PhD in 2007 in Earth Resources Engineering from Kyushu University in Japan. He also holds a business and management degree from the same university in 2010. He was awarded the GSPS, Japan Society of Promotion of Science, and the postdoctoral fellowship. And then he joined the Kyushu University as an associate professor in 2010, and now he's working as a professor at the United Arab Emirates University. Professor Saibi, his research interests mainly focus on exploration geophysics, geothermal energy, and geoscience. He has developed research groups on geothermal energy considering different countries from Africa, Asia, Middle East, and Central America. And I was very honored to be part of some of his research as well. He's a member of the International Global Geothermal Association and the Geothermal Research Society of Japan. He has published around 75 peer-reviewed journal articles. He's in 62 conferences papers up to date and 7 book chapters. He also has been invited speaker on numerous occasions at academic institutions through the world. and both national and international conferences. And today he's honoring us with a very special lecture about the potential geothermal resources in Algeria. Professor Saibi, please, the floor is yours.
Assalamu alaikum. Thank you very much for this presentation, Dr. Muhammad. And first of all, I would like to thank the International Network of Algerian Scientists, الشبكة العالمية للعلماء الجزائريين, for this invitation. Thank you so much. And thanks for the Algerian and international audience who are here online to listen to my presentation. So as you can see, today's talk will be about potential geothermal resources in Algeria. So I will give kind of a big overview about the geothermal resources in Algeria and all the studies that have been done in the past and recently as well, and what we need in the future to develop these renewable resources in Algeria. So this is the outline of my talk. We'll start with the introduction to give some basics and definitions about all the parameters related to geothermal energy in general. Then I will move to the historical of published works about Algerian geothermal systems. Then I will talk about topography and geological and seismic features of Algeria and North Africa as well. Then after that, we'll discuss the geothermal resources of Algeria, the different geothermal manifestations. Then I will highlight some geophysical techniques that we need to use to explore the geothermal resources. And then I will give also some used hydrochemical methods for geothermal investigations. Then I will talk about Geothermal Favorability Map of Africa, and of course, including Algeria and the North. Then I will show you some recent results with my research group about the geothermal energetic potential of some Algerian geothermal fields. And then I will talk about geothermal numerical modeling in general. Then I will end this presentation about what we need in order to develop and produce geothermal energy in Algeria. So introduction. So as you can see from this plot here, you have in the x-axis, you have 2010 running up to 2050. So here you have the history and here the projections. So this is the end-use energy consumption by fuel in the world. So now you can see that the world is growing, the population, we have population growth, we have economic growth as well, and especially technologies and all this industry. Many people are saying we are in the fourth industrial revolution. So we need much more of energy for our houses, our cars and schools and buildings and industry and so forth. And then you can see here that, of course, renewables is increasing, but still the world is taking its energy from hydrocarbons. But all of you know that hydrocarbons, they have facing some environmental issues like carbon dioxide emissions, the price, and other problems. And now many countries, they're looking or they're working or even started from the past to move or shift to renewable energies. Here you can see what happened in the last 2 years during the COVID pandemic. So we have more than 300 terawatt hour increase in renewable power generation, which is the largest ever. And we have minus 9% decline in oil consumption. This is the largest in the history. And we have minus 2 gigaton fall in carbon emissions. So we're taking CO2 emissions to lowest level since more than 1 decade. So these numbers are very important for today's talk. It means that the world is shifting, is moving to a new era. Of course, it started from the last 2 decades where we had this Kyoto Protocol, Paris Agreement. So all these international agreements, they worked towards decreasing the CO2 emissions and increasing the renewables. So our energy dependence is has many. We use energy for many things. Of course, for heating and cooling, for our factories, to run our factories, for transportation, as you can see, for aircraft companies, traveling, and of course for our technology, all our phones and tablets and computers, and also all these things, and also telecommunications and agriculture as well. So energy is very important for our daily life as human being. And then this is the question that many people, and especially people working in the oil industry, are talking about: how long before we run out of fossil fuels? So we have some statistics from the Free Energy 2010-21. As you can see, oil and gas will end after 50 years. And we have coal around 150 to 200 years. So it is the right time to transit to renewable energies, of course, including geothermal energy. So you can see that we have now many oil companies that are using oil and gas technologies for geothermal exploration and development. And we need to promote geothermal and other renewable energies at all levels, in the society, in the schools, at universities, in the research projects, and so on. And we need also to fund research on renewable, including geothermal. So we have different types of renewable energies. As you know, we have hydropower. This is from water. We have wind power, solar power, bioenergy, and geothermal, marine energy, and hydrogen. So today we'll focus about geothermal. Geothermal, it comes from the Greek word. We have here geo means earth, and therm means heat. So the geothermal means the earth heat. And geothermics can be defined as the study of the temperature distribution in the earth and the phenomena that influence that distribution. So we have this heat coming from the core and from the mantle and going up to the crust through these deep fractures, and then it heats all the water, the groundwater that we have in the crust, and then it creates boiling water, very hot water, and steam as well. And then we can use this technology, so we can take these hot geothermal resources from this production well, and then we take the steam, and this steam flushes the turbine, and then we generate electricity. And then, of course, the cooled water here is re-injected through injection wells into the deep geothermal reservoir. So it's a clean, renewable, and friendly, environmentally renewable energy. And there is no effect on the environment. So basically, this is, we have here, it shows the different internal structure of the planet Earth. So as you can see, we have the inner core, we have the outer core, and we have 80% of the volume of the planet Earth is composed of the mantle, and we have the thin crust, okay, the thin rigid crust here. So all the heat is coming from the inner core, outer core, and as well the mantle to the surface of the Earth. Especially if we check this figure here, as you can see, so we have this mantle. So you can see the very high heat flow is basically concentrated at mid-ocean regions, where we have this the meeting of tectonic plates, the subduction zones, and all these rifting zones as well. So all the places or boundaries of tectonic plates, we have increased or high heat flow coming from the subsurface. And the source of heat, basically, more than 30% from coming from Fourier heat flow from core and mantle, and the 70% is from the decay of radioactive elements in the crust, like uranium, thorium, and potassium. Here in this picture, you can see Larderello 1904. This is the first geothermal power plant in Italy. and it powered light 5 lights bulbs here. So what is geothermal reservoir? So a geothermal reservoir, basically, we have infiltration of cold water, so we need water. This is one of the parameters to create a geothermal reservoir. So this infiltrating water is cold, and then we have a heat source. This is also one of the parameters that we need for any geothermal system. Heat source could be very high, hot rocks, it could be a magma chamber, or we have deep infiltration of these cold waters. Then the water is heated from below, and then it comes up to the surface through the fractures, and we have these geothermal manifestations at the surface, like geysers or hot springs or fumaroles. And on the right figure here, you can see how the temperature is changing from the surface to the inner core of the planet. So when we reach, for example, the outer core, we have more than 4,000 degrees Celsius. And you can see here in the mantle, we have the high gradient. Okay, so all this temperature is coming to the surface at specific places, of course, in the world, and create these geothermal systems. So basically, to summarize here, for a geothermal reservoir, we need basically these three main parameters. We need the heat source from the bottom here, and permeable reservoir, and water, and of course we need fractures, high permeability zones, so the water can flow in both directions. So here you can see the different pictures for the geothermal manifestations. It depends on the fluids here. We can have just water, like in hot spring case. We can have just vapor for the fumaroles, or both of them, vapor and hot water in case of the geysers with high pressure. So different scientists, they classify the geothermal systems into categories based on the temperature. So basically, we have less than 100 degrees Celsius. It's called low or non-electrical geothermal systems. And above that, we can generate electricity. However, recently, with the development of technology, so we can generate electricity even with low temperatures, around, let's say, 70 degrees Celsius. In this slide, I'm showing the different geothermal power plants that we have, actually. So I can talk about these three. So the first one here, this is a steam plant using a vapor or dry steam dominated resource. So we have a production well here. So we produce the steam basically and direct it to this turbine. It turns the turbine here, and then we generate electricity, and we send electricity to the grid. And then the steam is condensed, okay, using this cooling tower here, and then injected through these injection wells to the geothermal reservoir. This is the first. And the second one, as you can see here, it's called single stage flash steam plant. It uses a water-dominated geothermal resource with a separator to produce the steam. So here, basically, if we have a geothermal reservoir, we have hot water and steam, so we use this system. So we have here a separator connected to the production wells that separates the water and the steam. The same story, we use the steam to turn the turbine and generate electricity, and the water here is cooled, and then the condensed water here from the steam also is cooled, and together they are injected into the reservoir. The third case, or the third type, is called binary power or organic Rankine cycle, which is good for low temperature geothermal resources, because here we're using another low boiling, another refrigerant like isopentane or A40 that helps to generate steam. So here we have the production well here. So we have the heat exchanger. So here where we have this, basically this liquid that helps to reduce the pressure and then reduce or lowering the boiling point, and we get more steam. And then we have the turbine here generating electricity, and then with the water, the cold water is injected into the deep geothermal system. So where we can find these geothermal regions in the world, or high temperature geothermal systems, basically they are located exactly at the plate boundaries, the boundaries of plate tectonics. As you can see here, we have North Africa, so Algeria here, North Africa, Southern Europe, Italy, for example, we have Turkey, we have Iran here, and we have the Red Sea, and we have East Africa here, like Ethiopia and Kenya and Rwanda here. We have here in Far East Asia, we have Japan, the Philippines, we have Indonesia, and we have New Zealand, and we have Iceland here. And we have also western part of North America. We have Central America. So basically all the countries, they have high geothermal resources. And we have also Western Southern America here. So this picture here on the top right, you can see the different tectonic plates that we have in the world, and you can correlate with the location of these high geothermal systems. So how much of electricity we are now producing in the world? So this picture is from 2005. Here you can see this table from 2020, from the World Geothermal Congress that was held last year in Iceland. So we're producing more than 16 gigawatt in total. So USA is the top in the list, more than 3,700 megawatt. We have Indonesia, the Philippines, Turkey, Kenya, New Zealand, Mexico, Italy, Iceland, and Japan. And from the last 5 years, we have these new countries. We joined this geothermal group like Belgium, Chile, Croatia, Honduras, and Hungary. Unfortunately, we don't have at the moment any Arab country. In Africa, we have basically two countries. We have Ethiopia and Kenya, who are producing much of geothermal energy. So here in this plot, you can see the installed cumulative capacity in megawatt in the world. Basically, the geothermal started after the energy crisis in the 70s. And you can see here, from 2010, the world produced around 12 gigawatt. And 2 years ago, 2020, it reached 16 gigawatt. So many countries are still developing and increasing the number of geothermal power plants to increase the utilization of these renewable resources. So, of course, geothermal is not just for electricity generation, but can be used for other applications. We have district heating and district cooling and snow melting, especially in cold countries or regions. We have spa and swimming pools, and we have greenhouses, and we have fish farming, and we have drying. So I will move to the historical of published work in about geothermal in Algeria. Basically, it started from 1988 and then 1989, as you can see here, the different years up to this year. So there are many works done by people from university, like USDHB University, Wargla University, and also Algerian who did their PhD in Japan, like myself, or Dr. Belhai Mohammed, and also CDER, which is a research center for renewable energies in Algeria. Okay, in Algiers exactly. So they did a lot of research. But basically, as you can see here, I put two colors here. You have green and red. So these red papers, let's say highlighted papers, basically focused on the chemistry of thermal waters. And in the green here, basically focused on application of geophysics to understand the deep geothermal systems. So this map, let's start with the topography. So Algeria is located in Northern Africa, is the biggest country in Africa. It has more than 2.3 million square kilometers. And the elevations, they range from the averages from 1,100 to 1,300 meters. We have basically high elevations in the north, which we call Atlas, due to the collision of Africa and Europe. And we have also high elevations in the south, in the Ahagar, where we have the highest point in Algeria, which is Ahagar, more than, I think, around 3,000 meters, due to the Pan-African collisional origin. Geologically speaking, Algeria, we have this Rift al Atlas in the northern part, which is the Atlas Alpine fault belt, and we have the Precambrian basement rocks. We have the Saharan Metacraton and West African Craton, and we have, which is exposed basically in the southeastern and the western part of, or southwestern part of Algeria. So as you can see here that Algeria has also very complicated geology and also many fractures and faults and active faults as well, because it's a seismic country, as you can see here from this seismic map. So the northern part of the African tectonic plate is a region of complex geology and dynamic tectonism, including active seismicity and recent volcanism. Now we go to the geothermal resources in Algeria. So Algeria counts more than 240 hot springs. So let me zoom here on the map. So basically the northern part, we have many hot springs. I will explain later in this presentation. So we have northeastern part, we have the north central part, and we have a northwestern part here. So we have hot springs, and we have also one, I think the second hottest hot spring in the world, which is Hammam. Hammam means hot spring. Hammam Salihin hot spring, around 98 degrees Celsius at the surface. If we check here the neighboring countries, so of course Morocco and Tunisia, they have some hot springs, and Egypt, especially in the Red Sea here. Okay, and if we check in Africa, for example, you can see here. So we have much of geothermal manifestations in the East African or the East African Rift system here, where we have Ethiopia and Kenya. Okay, and as you can see, the fracturation and the tectonic is also very important and increases the geothermal manifestations at the surface. And this plot here, you can see the how much Kenya and Ethiopia are producing from geothermal energy. Both are producing more than 800 megawatt of electricity, and then they're planning to, like in Kenya, they're planning to produce more than 5,000 megawatt, and Ethiopia more than 1,600 megawatt by 2030. And we hope that in the future we can see Algeria having its first geothermal power plant in the northeastern or northwestern part. So from this map, you can see that Algeria has basically 3 geothermal zones identified from geological and geothermal characteristics. We have the Tlemcenian dolomite in the northwestern part of the country. We have the carbonate formations in the northeast part of the country, and we have the sandstone Albian reservoir in the southern part of the country here. Of course, they have basically different geological settings, different climate as well. And even here, the Albion is quite a deep geothermal reservoir. This table shows the summary of the geothermal manifestations and the characteristics of these geothermal manifestations, and also estimated geothermal temperatures using geothermometry, for example, here. So Algeria, as I said, so on the northeastern part, we have the hottest hot spring, Hammam Maskhoutin, recently named Salihin, 98 degrees Celsius. And here you can see the chemistry is basically rich in chloride and sodium. And it has more than 90 megawatt per square meter for the heat flow. And the geothermal reservoir was estimated around 71 from this reference. The geology is basically carbonate rocks. So as you can see here, all the geothermal manifestations in Algeria are basically used for bathing. You can see the northwestern part, we have Hammam Bouhjar and Hammam Bouhnifia, 68 degrees, and Bouhjar even more, I think, with basically the same chemistry, rich in sodium chloride and sulfite and bicarbonate, heat flow more than 120 megawatt per square meter, and deep geothermal reservoir temperature was estimated using chemical analysis with more than 100 or less than 133 degrees Celsius. The rocks are mainly evaporitic, a carbonate sequence, and used for bathing. North central region, we have Hammam el-Biban with 80 degrees Celsius, and the southern part, basically, the temperatures are lower, around 40 to 50 degrees Celsius in the southern part. So here you can see the Hammam Salihin in northeastern part of Algeria here in Khanchla Wilaya, Wilaya Khanchla. It's ancient Roman bath, so it has a long history. And we have here Hammam Bouhjar in northwestern part of Algeria, located in Ain Timoshent, Wilaya de Ain Timoshent, northwest. And also they have a thermal station here, so people, they can go and use these hot waters. So I checked recently the news coming about renewable energy, especially the geothermal, using this this website, Think Geoenergy, which has all the information related, or publishes all the information related to geothermal worldwide. And you can see Algeria, we have from 2015 until recently, we have many projects, especially for greenhouse projects in Wargla, and also the Algerian government started energy transition plan from 2021, and they had also a workshop last year about geothermal energy, the substitute for natural gas. So there are many things ongoing in the country, and this is also worldwide. So we need to move to these renewable energies. Now I will move to geophysics and how we can use geophysics to delineate or to investigate the deep geothermal reservoirs. So I will start with magnetotelluric, MT for short. This is electromagnetic geophysical technique that can be used to image the Earth's electrical resistivity structure from depths about few hundred meters to several 100 kilometers. And this technique is basically based on Maxwell's equations and uses very high frequency and low frequency for shallow and deep investigations. And it's one of the best geophysical techniques that can be used for geothermal exploration. Basically, we have 4 electrodes here, and we have 3 magnetic coils, and we measure the natural electrical and magnetic field changes, and then from that we after some calculations and inversion, then we can estimate or calculate the resistivity of the subsurface. So basically, for the empty workflow, we start with data acquisition in time series, and then we during the processing we convert the time series data to the frequency domain, and then we do the analysis of the data. We check the dimensionality of data, the strike angle estimation, the static shift correction, to know if the model or the subsurface geology is 1D, 2D, or 3D. Then we create our subsurface model using inversion tools. And then after that, we compare this model with other existing information, geological data, well data, and also we can do what we call joint inversion with other geophysical technique or data to enhance our model. Here I'm showing you results from my research team. We have here in UAE, Al Ain, they have some hot springs. In Al Ain and Ain Khat, the temperature is around 45 and 40 degrees Celsius. And here you can see the empty stations here. And this is a cross section, a 2D model. And we can find this geothermal reservoir here. Here, another case in Gisenyi geothermal field in Rwanda, in this area, acquisition of MD. Here you can see the empty station.
Well, I think we have technical.
I think we are having some.
Yeah. We'll try to.
Yeah, I think we have some technical problem. Please wait a little bit. We will try to join Dr. Saibi. Professor Saibi probably will joining us shortly. Please wait. So I remind you that we apologize. We are having a technical problem from Professor Saibi side. We hope you're going to join us shortly. So I apologize for the technical problem. I hope Professor Saibi will join us very soon. Please hold 1 moment, please. Okay, so we apologize. It seems that Professor Saibi have some technical problems and he has to restart his computer shortly. So probably he will be back in few minutes. Actually, the idea behind this webinar is to present what is being done or what have been done in the geothermal energy area. So Professor Saibi Hakim is thermal energy and geophysical data for geophysical on many geothermal projects in Japan. And now he's also published many papers on geothermal potential in Algeria. So far, he introduced the basic concepts of the geothermal hot springs or hotspots in Algeria. But and from now on, hopefully he will be back soon. He will discuss more about the geophysical side of it. Please wait a moment. Okay, I think, hi, Professor Saibi, can you hear us?
Yes.
No problem. So we apologize for this technical problem, and I think now we got him back, so we can carry on. So I think we stopped on the slides showing the magnetotelluric data in Rwanda and in the United Arab Emirates. So you can carry on from that slide.
Okay, sure. Thank you.
Please share your slide.
Yeah, I think from here. Good. Okay, so yes, I said about magnetotelluric technique. So here you can see.
Well, I'm sorry, we can't see your presentation, sir. Can you share your screen?
Can you share your slide? We can't.
Sorry. Yeah.
Yeah. Can you please share your slide, Professor Saibi?
Okay, it's coming. Is it okay?
Excuse me.
Yes.
We can see the slide, Sir Hakim.
Again, sorry, Mohammed. Yes. Can you see the slide?
Screen.
I shared my screen. Is it okay now?
No.
Did you share the screen?
I can't. We still have the problems. There's no. Try to use maybe.
I'm sharing the screen. Can you see?
No. We can't see the screen right now. Maybe Dr. Amrouche will give you access or something like that, because I'm not a moderator in this. Don't have the. Let me try something. Try to use the same process that you used before to.
Can you see my screen now?
No, we still can't see your screen. I don't know. I'm gonna contact Dr. Amrouche. Maybe he also have connection problems. Just 1 second, please.
Okay.
So he's fixing some issues and some problems with the screen. So just wait for a second, please.
Okay.
To the audience. Thank you.
Thank you.
we think we can see your screen. Try to open the PowerPoint. Just redo the steps that you did just this moment. Press on the share screen just in the bottom of the StreamYard.
Hello. Sorry.
Can you see my screen now?
No, but we've seen your screen before. Just a second before. Can you just press the share button just below the? It's the.
Yeah, I did that. Huh?
Okay.
I think we're good. Can you? I think
okay, now it's crystal clear.
You can see your screen. Okay. Please go ahead.
Okay, it's fine. Okay, so I was talking about magnetotelluric, which is electromagnetic technique, and I'm showing some cases from the UAE and from Rwanda. You can see here in UAE they have some low temperature geothermal systems in Al Ain, Abu Dhabi Emirate, and Ras Al Khaimah. We have Ain Khat here, hot spring, and using MT we could image the subsurface electrical resistivity distribution, and we can see the geothermal system here, or reservoir. And the same case also in Rwanda. So we have here the magnetotelluric stations, and using the 3D inversion, we can image the geothermal reservoir and even the heat source and the conductive zone. Next, you can see this good example from Ayurveda geothermal field in Ethiopia, located here. So we have a huge, good data set of magnetotelluric. And using 3D inversion, we can image the 3D resistivity structure of the geothermal reservoir. And we found two reservoirs, Reservoir 1 and Reservoir 2, and the heat source, and also the cap rock. So this is the main characteristic of the geothermal reservoir. So basically, we have the heat source from the bottom, and then we have the geothermal reservoir, and we have the cap rock or the smectite minerals, which has a low resistivity. Also, we can use potential field data, so like gravity and magnetics. We can use the CG6 gravimeter, for example, or from Syntrex company, we can use magnetometer. After recording the data and the corrections, we can do 2D filtering and 3D forward and inversion modeling. It will help us to locate the edges, the faults, the intrusions, the basement rocks, and so on. And then we can also do the joint inversion, for example, with MT data. It will help us to better understand the subsurface setting of the geothermal systems. Here you can see a good example. This one is from Ethiopia, from Aluto Langano geothermal field, using gravity data inversion. And here you can see the wells, or geothermal wells. And we see a good correlation between geothermal well data and inverted density model, because from gravity we get density model here. And you can see the isotherms here. Also, we have a good matching. And another example is is from the UAE. So here we have two hot springs in Al Ain city, located eastern part of Abu Dhabi Emirate. So also from gravity and magnetic data, we can construct 3D density model or 3D magnetic susceptibility model. So all the geophysics here, it helps us to understand what is the geothermal reservoir, what is the heat source, what is the cap rock, and the fractures, the faults, and the basement rocks, and so on. So it's very important phase for any geothermal study. Next, I will go to a different technique that we use also in geothermal, which is applying centroid or diffractal, which is the newest method for calculating Curie depth, temperature gradient, and heat flow. So here we use magnetic data, so we can use aeromagnetic data, and we have even satellite magnetic data, which is available. So using this data, we can calculate the power spectra, and we can understand the depth to magnetized source. And from that, we use this understanding, so we detect the magnetic layer, and we can detect also or calculate the Curie point depth. So in general, at the base of the crust, where the temperature is very high, so the magnetite minerals, they lose their magnetization at a temperature roughly more than 580 degrees Celsius. So using this power spectra, so we can understand the depth to the top of the basement rocks and to the bottom of this magnetized body. And then from that, from the Curie depth and the Curie temperature, which is 580 degrees Celsius, we can use other equations to calculate, for example, the heat flow and the temperature gradient. So this is an example from North Africa. You can see Algeria here, and this is total magnetic intensity map of Algeria here. The values basically, they are from negative 400 to plus 370 nanotesla. And we subdivided the country or this region into windows of 1,000 kilometers. And then for each window, we calculated the power spectra. And then from that, we can estimate the heat flow. And the heat flow here, you can see here the values of the heat flow ranging around 60 to more than 100 megawatt per square meter. We have high heat flow basically in north and west, and also in the southern part of the country. We did a comparison between calculated heat flow and measured heat flow from wells, and we found an excellent correlation with a coefficient equal to 0.99. And here, this map is showing from this paper, recent paper published this year, it's showing the Curie depth and heat flow from Africa, basically. And if we focus in Algeria here, we have basically two parts. In the northern part, the Curie depth is around 38 kilometers, and the southern part is lower, thinner, with 26 kilometers. The heat flow in northern Algeria is around 61 megawatt per square meter, and in the south is much higher in the Hoga region and reaches 83 megawatt per square meter. The surface heat production in the north is between 2.8 to 3, and the mantle heat flow is around 30 to 32 megawatt per square meter, and the geothermal gradient is around 22 to 22.8 degrees Celsius per kilometer. However, the southern part, we have the mantle heat flow 57 to 64 megawatt square meter, and the near surface geothermal gradient is around 27.1 to 28.8 degrees Celsius per kilometer. So basically, we have in the northern part and also in the Hoga region, these places, they have quite a huge geothermal potential. So we can use also remote sensing techniques. We have many satellites around this planet, and from this satellite, we can get information, for example, about land surface temperature distribution on the ground. Here, this is an example from the UAE. So we can have estimation about the temperature, about the heat flux. So all these parameters are important for any geothermal study. I will move to the hydrochemical characteristics of the Algerian thermal springs. Basically, for any hydrochemical application, we have here geothermal reservoir, we have faults, We have cold water and hot water. So basically, we estimate these chemical components that we get from the hot water or from the gases like calcium, magnesium, sodium, potassium, bicarbonate, sulfate, chloride, manganese, lithium, and so on, and gas chemistry and even isotopes. And from that, we can use this method like geothermometry, mixing models, heat and mass balance equation. And from these techniques, we can understand the temperature, for example, in the deep geothermal reservoir here. We can also understand the chemical composition of the deep geothermal fluid and the depth, which is also very important, of the geothermal reservoir. So combining the geophysical results and the hydrochemical results and the surface geology, and also from well data, we can construct what we call a conceptual model. And then from this conceptual model, we move to the last stage, which is the numerical simulation. And here you can see the geothermometry. These are the equations that we can use to estimate the temperature of the deep geothermal fluid. We have cation and silica geothermometers. You can see here the equations. These are from this paper, 2009. We estimated the temperature at Hammam Salihin hot spring. As you can see, the discharge was around 94 degrees Celsius. And here you can see the temperature of the deep geothermal reservoir. So basically, northern Algerian geothermal systems are basically structurally controlled systems. We have deep fractures and deep faults. Then we have deep penetration of the cold waters heated from below with the conductive heat and coming back to the surface. And in the southern part, we have basically a basin geothermal system, which means we have conductive heat and we have these very thick basins. For the geothermal favorability map, so we can use also what we call geographic information systems, or GIS. Here we combine, I give you here an example from Africa. We combine different types of geoscientific maps, for example, elevation, gravity data, magnetic data, seismic data, heat flow data, geothermal manifestation data, and geology. And then we assign a weight for each layer using this method. It's called weighted overlay method. And then we integrate all the thematic layers on all the data, and then we come out with a geothermal favorability map. So here we have basically this, you can see 5 colors, and the red one, it shows the very high geothermal potential in Africa. So we estimated around 14 regions from northmostern part of Africa, from Egypt, Red Sea access, Liberia, Djibouti, Ethiopian rift here, and Kenya. Then we have Lake Albert Rift here in Uganda. And we have, for example, Lake Kifun Rift, Tanzania Rift, northern Malawi, central Zambia, and Botswana, and then Namibia. So if we focus here on Algeria, you can see, let me show you here. So basically, the northern part has quite huge or high geothermal potential. Now let's move to this also interesting result about how much of electricity we can produce from some Algerian geothermal fields. So we use this stochastic Monte Carlo simulation. It's called GPP eval. It's a Python code developed by Pokasangare and Fujimitsu in 2018. So we can calculate the geothermal stored energy in a volume using different parameters from the surface and the subsurface. So we use to calculate the power, we need information about the density of rocks, density of the fluids, the porosity. Then we need the depth to the reservoir. We need the area of the reservoir and the volume and other parameters related temperature of the geothermal reservoir, temperature at the surface, and other parameters related to the power plant. So as you can see here, the reservoir area, the thickness, the abundant temperature, the reservoir temperature, and these parameters, the porosity, rock-specific heat, water-specific heat, rock density, and water density. And for the surface, we use the heat recovery factor, the conversion efficiency, the power factor, and we can do the simulations for lifespan, let's say 25 years or 50 years. Then we can estimate how much of megawatt electricity we can produce from any geothermal system. So here, this is the starting. We need to put our data here in the simulator. Then we do the iterations. Then we generate results, and then we can show the results like this. So here you can see the input data for the Hammam Bouhjar and Hammam Salihin hot springs, the different data. Of course, this data can be updated if we have well data, if we have results from geophysics. So this data can be updated, and we can have better results. So here you can see for Hammam Bouhjar, for example, here is simulation for 25 years and another one for 50 years. So for 25 years, we can produce around 4.4 megawatt of electricity. And for 50 years, we can get easily 2.2 megawatt of electricity. And here from Hammam Salihin, we can get for 25 years around 7.8 megawatt of electricity and around 3.9 megawatt of electricity for 50 years. And then after that, we need to develop what we call geothermal numerical modeling. This is also very important. This is the workflow. So we need to gather all this information, starting from the conceptual model based on geological understanding, structural understanding, well data, geophysical results, hydrochemical results, and so on. And then we create a 3D model, and then we put the heat source, and then we simulate it in steady state and then transient state using, we have different simulators, commercial simulators, which some are free and others are not, like TAF, Eclipse, Hydrotherm, NREL, and Petrasim. So we can see the distribution of the temperature and the pressure and the vapor inside our geothermal system. And then we can even do some scenarios, for example, having wells, production well, for example, and these are injection wells. And then we can change the mass, how much of water we take and how much we need to inject to keep the sustainability of the geothermal reservoir. So all of this can be done using these simulators or geothermal numerical simulators. So at the end, what we need in order to develop and produce geothermal energy in Algeria. So from this presentation, you can see that Algeria has a huge, considerable geothermal resources, more than 240 hot springs with high temperatures that can be used for direct use applications, or GSHP, which is ground source heat pump, and electricity generation. So to do this work or to reach this target, we need a teamwork. So people from different backgrounds, engineers, geoscientists, geophysicists. I'm sure that Algeria has many excellent engineers and excellent experts in different fields, so they can work together. And we need a good geological survey, a good structural geological survey as well, and new hydrochemical analysis, so we can combine with geophysical explorations, especially with magnetotelluric and also other geophysical techniques. And then we can create a conceptual model and create then after that a numerical model. And then from this understanding, we move to the finance analysis, and then we can decide which power plant we need, how much of electricity we need to produce, and then I think this is the end of my presentation. Before ending, I want to mention that Algeria is an oil producing country, so we need to use this technology from abundant oil wells or produced water from these oil wells, so it can be used for generating electricity as well. So thank you very much for your attention and listening, and sorry for this internet disconnection. Thank you.
Thank you, sir.
Thank you very much, Professor Saibi Hakim. It was a real pleasure to have you, and thank you for the very insightful presentation. I think you covered most of the basics of geothermal exploration, and you really developed in details the Algerian potential of geothermal exploration. And you can see all the references are dating 2020 and 2021 and 2022. So this is quite new studies you are sharing with us here. So I would like to apologize to our audience about the technical difficulty we had during this presentation, again, from my side and from the side of Professor Saibi. I think we will move to the Q&A session now. I remind you, if you want to ask questions, you can post your questions in the comment section in Facebook and YouTube or in LinkedIn. Unfortunately, we lost connectivity with LinkedIn for the comments, so I will just pick up start with one question from LinkedIn that we cannot display here in our platform from Mr. Mohan Sadiq Aysat. He's asking two questions. He said 282 hot springs were announced recently by the renewable energies officials. What would be the GW, the gigawatt potential of such geothermal sources? What is the cost of such power generation installation? Professor Saibi, do you have any number of the potential in GW? I think you showed some studies recently published about the potential of in GW. What would be the cost?
So in terms of electricity, I did just the simulation for two important hot springs in Algeria, Hammam Bouhjar and Hammam Salihin. So these two, for 25 years, we can produce for both of them around 11 or 12 megawatt electricity. I don't have information or answer for all Algerian geothermal fields, but basically we need more exploration, more geophysics, more investigations, and then we can understand how much. Of course, roughly we can have these numbers, but of course, these are basic numbers, so we need more investigations. In terms of money or cost, of course, geothermal, in the beginning, when you install the power plant, the exploration studies, the drilling, it has a cost. So you need to put some money, but for the running cost, it's going to be very low and very competitive to other energetic sources.
Thank you very much. So, Qamruddin, can you read the questions from YouTube?
Yeah, this question is from Abdel Fattah Brazil, where we can find some parameters for make a heat transfer and fluid circulation model for reservoir, for example, in Algeria.
Again, can you, again, the question, please, can you read it?
Where we can find some parameters for make heat transfer and fluid circulation model for reservoirs. He gave an example in Algeria. Can you give some examples from Algeria? Or can I repeat the question?
I don't understand this question clearly. Which parameters do you mean?
Like heat transfer and fluid circulation models.
Yeah, he's talking about models of heat transfer models and fluid circulation. Is there any data available for Algeria?
Well, I'm working here at the moment. I left Algeria almost 20 years, so I don't have access to any data. So, well, first you need to check the published papers. This is the first access to any data. But for my case, as you can see, I'm using satellite data. I'm using published data, and also as a geoscientist. So if we have carbonates, for example, or we have limestone or granite, so we have some, if I want, for example, to check, let's say, thermal conductivity of any specific rock, so I can use some literature data as well.
So We can't hear you. So the next question is from Mr. Hussein Abdullah. Feeling that some hot springs within Tassili Najjar, not in the inventory. I don't quite understand the.
Yeah, maybe some words about the south geothermal potential in the desert, Tassili and Najjar. Is there any? I think you mentioned that it's a quite interesting place for geothermals. Do you have any idea about some potential there?
Yeah, it's a good question. Actually, I don't have much information about geothermal manifestations in the southernmost part of Algeria. However, from the satellite magnetic data after using the diffractal method, we found out that the crust is thin. I guess there is a hot plume beneath that area, and it's very hot. So the problem is we need water. So it's a good place maybe to develop what we call HDR method, hot dry rocks. So we need to inject the water with high pressure to create the fractures, and then we can get this hot water and use the power. So this is maybe one of the applications. But unfortunately, I don't have much data about this region.
Thank you very much, Professor Saibi. We will pick up the next question again. Can you go for it?
So the next question is from Sidulad. Is an average of 7 megawatts of Hammam Salihin a lot? How does it compare to other averages in the world? And what energy need can we cover with that much production?
Yeah, it's you have to check. I said 7 or 4 or 12 megawatts for 50 years or for 25 years. So basically, it depends on your usage. So it depends. This is also it's a cultural related question. So if I take let's say American houses, so 1 megawatt can let's say support or around let's say 800 or 900 houses. So it depends on your house size, how many rooms you need. It depends on your electricity usage and so on. But we need to start. This is the problem. So we have to start with one geothermal power plant, and then we will see. It can be used also for schools, for hospitals, for many facilities as well.
Thank you very much, Professor Saibi, for your response. I think we still have a few questions, but I don't know if we're running out of time. We are already exceeding 1 hour. So probably, Qamruddin, do you have any final question before we close this meeting? A personal question about geothermal exploration?
Yeah. Thank you very much.
I think you're very motivated to work on that.
Yes, of course. Especially in the Hammam Squatin, recently named Hammam Salihin. I'm doing research. So is there any geophysical data or, for example, drilled pilot holes? So being low enthalpy, most of the geothermal energy, geothermal resources in Algeria are low enthalpy. Can we produce like power electricity from those binary cycles? And is it scalable? So for all the Algerians, for example?
Okay, thank you. So for actual data, I don't know. I'm sure that CDUR, they have this data. And actually, it's not, in my opinion, it's not low enthalpy. So as you can see, we have the second or even the hottest hot spring in the world. So it's quite a high potential. And with recent technologies, as I said in my presentation, even with low temperature, we can produce electricity. So I'm sure, like in Hammam Salihin or Hammam Bouhjar, we can pick up 2 or 3 regions. We can easily install a power plant and produce electricity.
Thank you very much for your answer, sir.
Okay, thank you very much, Professor Saibi, for your very insightful presentation and for responding to our questions. It was a very, very interesting database we have in here, and even from your presentation, and especially recently published data. I'm pretty sure that all the audience will appreciate reviewing this. I remind you that you can see the recording of the presentation after this call. So we reiterate our sincere acknowledgement to Professor Saibi for his time and dedication for contributing in this project. And we are going to have also, I remind you that this is a series series of webinars where we have each month one specialist in specific field, and hopefully next month we will invite another specialist about the energy domain in Algeria. So please keep in touch with our INES webpage. With that said, I would like to thank all the audience for participating. We also thank Professor Saibi Hakim for his very, very insightful presentation. I'm pretty convenient that there is a lot of potential, a lot of studies that can be done in Algeria. You know, it remains empty zone, and a lot of things can be done in this direction. So we thank you very much, Professor Saibi. Thank you, Qamaruddin, for your support, and looking forward to see you on the next event. Thank you very much.
Pleasure. Thank you very much.
Thank you. Yalla, salam.